distributed training is the actual solution that quickens the pace of training for neural networks by using a cluster of GPUs during training. So when a model is fine-tuning hyperparameters, model parallelism based training modules looks through multiple configurations at the same time. Gradient descent. And it's a rock star in data parallelism. But here's the catch, like using small batches and memory division techniques can lead to GPU memory issues. So we need to talk about here about other methods like batch sizes. You have got keep them large enough to keep GPUs happy. We are talking about multiple GPUs on a single machine, nifty GPU drivers to make everything run smoothly and enabling them and enabling that they are able to perform internal GPU communication. Okay. Assalamu alaikum everyone. So far now. We are diving into the exciting world of data and modern parallelism. And before moving forward, let's bridge the gap between our past discussion and what we'll be discussing now. So, as we already discussed, the pre-training and fine-tuning modules of LLMs with their feature sets. As we know, training in LLMs require a lot of computational power and memory, like they can't even fit entirely into the memory of a single machine. There comes for the solution of that problem, there comes the data and model parallelism that will help us to solve this problem, which we will discuss in further slides in detail. Now moving towards prerequisite and objectives. But before we jump in, let's make sure we have got the basic knowledge to handle this problem. You need to have some grip on Python programming and a bit familiarity with NLP, all machine learning, and LLMs. Also, don't forget about the nuts and bolts of infrastructure and costs regarding the training. It's all part of the game. So now we will talk about our goals. What will be our goals? Simply, okay. Here we are here to learn about distributed training. That will be only possible if we wrap our heads around different types of data and model parallelism and can uncover the best strategies to make sure that these techniques shine together. Then we have agenda. All right. Uh, uh, so that will be the overall agenda behind the whole lecture that will be present here. Starting from the introduction of data and model parallelism, we will introduce you distributed training. Picture this like you are training LLMs like models with parameters in billions in higher counting numbers with a massive data hungry computational hungrier power than a toddler like a simple large language models. Like these types of models are unable to train to the platform with limited resources in terms of GPUs and hyperparameter. So what the solution like? How we will solve these kind of problems? Thus, distributed learning or distributed training is the actual solution that quickens the pace of training for neural networks by using a cluster of GPUs during training. So when a model is fine-tuning hyperparameters, model parallelism based training modules looks through multiple configurations at the same time, which makes it faster. It's like a teamwork for models. Imagine breaking down the training process and having different devices tackle different parts of it, not a single device. Multiple devices will be utilized for this purpose. Those devices could be CPUs or GPUs, and together they are unstoppable. This isn't just a tech buzzword, it's how we are making language models understand us better than ever, like by solving the relevant problems regarding all of different matters. Then, then now we will discuss like why we dive into the distributed training when we have some other resources for this purpose as well, and how this will become to all problems mentioned previously. Okay, well, let's consider this as language models get bigger day by day. So do their appetites for computational powers. That mean that centralized training mechanism won't compete anymore. Distributed training is the hero move here. It's nothing like we are adding some additional components and resources in it. It's like we are using our resources efficiently, like by spreading the similar load across multiple devices instead of a single unit, and that will ensure scalability and tackle those beastly LLMs, large language models, head on. Plus, it also helps us deal with memory limitation, complex architecture, and makes our training process super efficient. Then we have then we will talk about the tactics of how this type of distributed training will perform. There are two major branches of distributed training: data parallelism and model parallelism. Let's start with the data parallelism here. Imagine you have got a hefty data set and you're like, let's try to break it into pieces. Each piece goes to a different GPU, and these guys tries to crunch the numbers simultaneously. They try to chat and exchange gradients among themselves. And finally, you have got yourself an average gradient for the whole gang. It's like teamwork at its final, all for one model. So remember. So let's chat about training strategies which will be implemented in data parallelism techniques. These are synchronous and asynchronous, as mentioned in previous slide in data parallelism. In the synchronous kernel, everyone got a copy of the model and they all move together. Think of it as a choreographed dance of calculation. But remember, sometimes even the choreography part will be unable to trigger a good dance performance, like it's hard to coordinate, especially when devices have different speeds. Each device differ in its choreography, each device will be differ in its speed, maintenance, capabilities, and output vectors as well. That's where asynchronous training steps in to help us. Here, each device do their own thing like their own individual basis, like a dance party where everyone grows to their own beat. No one needs the choreographer, no one needs the dance steps and guidelines. It's messy and can be better fit for such kind of scenarios which will be handled during distributed training. Then we have data parallelism validity. Let's move on and talk about a tiny glitch in the matrix. It's called stochastic gradient descent. And it's a rock star in data parallelism. But here's the catch, like using small batches and memory division techniques can lead to GPU memory issues. So we need to talk about here about other methods like batch sizes. You have got keep them large enough to keep GPUs happy. Like you don't need to divide them into small chunks. You have to keep them in large sizes, but similar to keep them at an equilibrium state. That means the memory distribution also needs some stability in itself. Otherwise, your training might hiccup. But don't worry, there are tricks for that problem as well. Like larger batches or even using the entire dataset for those gradient exchanging opportunities. So now it's the right time to meet the other branch of distributed training, that is model parallelism. Imagine a model is so massive that it can't even fit on a single GPU. That means we need to talk about a rockstar with a full entourage. Like each part of the model get its own GPU and they work together like a dream team. Like a new dataset is the module was created that is now for that purpose. We have some examples like a new dataset in this module that was created for that purpose, and it is known as pile that include 22 different high quality dataset in itself. It's a combination of existing data sources and new datasets in the range of 825 GBs. It's like you are solving a puzzle. Each piece fits perfectly through the forward and backward propagation techniques, like a well choreographed dance all across will settle down properly and accurately all across these GPs. Now, ready for the nitty-gritty of implementation. I mean to say that we are moving towards the implementation part. Let's talk about setting up something for distributed training. We are talking about multiple GPUs on a single machine, nifty GPU drivers to make everything run smoothly and enabling them and enabling that they are able to perform internal GPU communication. Okay. Then we have management resources, like managing resources, making sure GPUs are fully utilized. It's like throwing a party and making sure everyone having a blast. And we are not forgetting about those distributed environments. It's all about teamwork, even on the hardware form, which include data parallelism, data preprocessing, and data loading efficiency as well. And now let's talk about the implementation strategy in different scenarios, like which is better and how we will use each one of these strategies on its own. In the context of LLMs, we will start with the single GPU. In the context of LLMs, like AI text scenarios, a single GPU is utilized for both data and model parallelism. In data parallelism, it involves splitting the training data into batches and processing them concurrently on the GPU by enabling faster training. On the other hand, model parallelism involves dividing the model into sections and allocating each part to the GPU for efficient computation. In this whole scenario, a single GPU handles both data and model parallelism to enhance training speed and efficiency. Then we have single node with multiple GPUs. When dealing with a single machine equipped with multiple GPUs, data parallelism becomes more effective. The training data is divided into batches and distributed across the GPUs, which simultaneously process them. Additionally, model parallelism can be applied by dividing the model into segments and allocating each part to a different GPU. This overall approach increases both the speed and the capacity for training LLMs. Think of it like a distributed party. Everyone is having a fun, but with the right strategies to settle the things that can really heat up the whole the whole scenario. Now let's come towards the scenarios where multiple machines are connected in a cluster, like we have multiple nodes with multiple GPUs. A combination of data and a model parallelism is also employed as well. Like data parallelism spreads batches of training data across GPUs within each machine, while model parallelism distributes different segments of the models across different GPUs. Moreover, the training process can be distributed across multiple machines where each node contributes its GPU to jointly train the LLM. This whole setup significantly accelerates the training items and enables us to handle even larger and complex LLMs through efficient data and model parallelism across a network of GPU, not a single, not multiple, but a network of GPUs. Now it's time to solve it's time to discuss some advanced parallelism techniques. Even ever thought about Have you ever thought about mixing data parallelism and model parallelism together? It's like combining chocolate and peanut butter together. They just well work together. Hierarchical model parallelism is the secret sauce for these all type of cognitive models that doesn't mess around. And guess what? Efficient communication between devices is the key of this whole asset. Think of it like passing notes in class, but super high tech. All right, let's see these strategies into actions. Training large scale models. We have some strategies like training large scale models will tackle big data, crafting top notch models, and even fine tuning. It's all possible with distributed training. Now it's time to wrap it up with some multilingual and multimodal magic, and you have got a recipe for success here. So here, the lowdown. Model and data parallelism are your main assets in training large language models, especially in distributed training, especially in beast type of large language models. They are like Batman and Robin, optimizing hardware and taking our language understanding to the next level. And here we are done with whole concept of data and model parallelism.